Let's start. I have done the register. Just make sure on the Beacon app it's what you expect. So pay attention to the board. You're going to see TCP header. If you just compare TCP header against UDP header, which is shown here, what can you tell me just from looking at it? What can you tell me with regards to the size? One thing.
There's more fields in the TCP header.
Great. So TCP header is known to have 20 bytes overhead, whereas UDP header has 8 bytes overhead only. TCP header is heavier. And if you think about it, it should be heavier because TCP takes care of functionalities and tasks that UDP is not aware of at all and does not care about at all. Yeah. So TCP is known to be a stateful protocol. So all these terms, they have specific meanings around them. Yeah, stateful, connection oriented, things like that. So stateful protocol in a sense that it keeps track of the state of the protocol. State in this regard, in this context, think about that session establishment, taking care of that session that controls the actual data transfer, or terminating that session later once the actual transfer of data was taken care of. So you have source port and destination port. Those are two applications associated to those ports. So on the sender side, the application is associated to source port, some number, and on the destination side, that application is going to be associated to some number again. Then you have sequence number and acknowledgement number. With sequence number or acknowledgement number, we keep track of what we have sent and what we have received. Yeah, if I send you segment 30 of big chunk of data, then that sequence number is going to be 20. If I am sending you segment 1 through 10, but you only have received segment 1 through 8, you didn't receive segment 9 and segment 10, then you're going to acknowledge back to me with acknowledgement number 9, not 8. Because acknowledgement number always refers to what I expect, which is 1 more than what I have received. Yeah. So once again, if I send you segment 1 through 8, segment 1 through 10, but you only receive segment 1 through 8, not 9 and not 10, you send me acknowledgement number 9, saying that you have received up to 8. Now you're expecting 9. 9 is the one which is missing. Yeah, so acknowledgement number is always referring to 1 plus what I have received so far. Header length and reserved. Header length and reserve, as the name suggests, we are not caring about at the moment, but our focus is on that thing, that box, that field in the center, control bits. 6 bits as control bits, known as flag, TCP flag, or TCP header flag, or flags, because each bit within that field is a flag, is a single flag. And by setting that flag, meaning putting that bit 1, or resetting that flag, meaning putting that bit 0, you're going to send and receive some you're going to send and receive some important notifications to the other part of TCP communication. Then you have a window and window size field, basically 16 bits there to tell you the size of the window. Window size has to do with that flow control that I told you earlier. Remember, I told you that TCP takes care of flow control in the sense that it can control the rate at which you're speaking. This is taken care of by these windows. Checksum, yeah, over the TCP header and data to find out where the errors are. Checksum or similar mechanism, if you think about it, we didn't have that in IP. We didn't have that in network layer. We did have that in data link layer with Ethernet trailer. You remember within Ethernet trailer, we had FCS, frame check sequence, CRC, cyclic redundancy check inside FCS, yeah? So we had a mechanism for error detection. Here at transport layer, we had that with checks. Urgent and options are not our focus here. If you think about it, as it says on the right-hand side, it's 20 bytes. So 16 bits, top left source, port, 16 bits, destination port. So each row is 4 bytes. You have 5 rows, 5 times 4 becomes 20 bytes. This 20 bytes is going to be added to each and every single segment, not datagram. Yeah, we are talking in the context of TCP, that you're going to send and receive. I believe I have covered mainly what this table is going to tell you about each of these fields and what they do. Just remember, checksum covers the TCP segment header as well as TCP segment payload, which is the data inside. Now, UDP, the name suggests, UDP stands for User Datagram Protocol, much simpler and more efficient in a sense that it's faster compared to TCP. Can we have a scenario whereby I have speed of UDP as well as reliability of TCP together? If you care about speed, use UDP and ask higher layer of OSI, which is session presentation and application, or TCP/IP, which is application, to take care of reliability. So if you are after the speed that UDP provides for you, and that's the case, by the way, for many protocols, especially the ones that user develops themselves, like new protocols, if they care about reliability as well as the speed, they use UDP because UDP is faster, but they let application layer itself to come up with a mechanism to take care of reliability. Yeah. Being fast, having smaller header size means that it's a best effort delivery. There is no acknowledgement process with UDP. Therefore, it's like ordinary mail when you send a letter with your hosting system, but you just place it in the order in ordinary mailbox, not first class, not Royal Mail first class. So you just send it and you receive that the destination is going to receive it. You don't know when the package will be delivered. You don't know when the postman gets to that address if the recipient is present there or not. Once it's been delivered, you don't know if it's been delivered or the guy has opened up your message. This is all UDP. Whereas TCP is like first class Royal Mail, where it is tracked in the sense that you know when it's been delivered. You know if the guy was present there and has signed for the delivery, has received it. Thank you very much for being on time. Thank you very much for being here in 10 minutes. And by the way, that happened 3 weeks so far. I don't want to see it happen again. Yes, Salvatore, Leon, Luca, and others. Yes, I know every week is either toilet or food, but I don't want to see that happen again. So either eat or drink before or after, or go to toilet before or after. Can't go like this. So UDP header, much smaller, more efficient. So you care about source port and destination port similar to TCP. You need to know which application is associated to this conversation. Where should I deliver this message to? Is it a browser? Is it my online chatting application? Whatever. Length and checksum. That's it. No sequence number. No acknowledgement number. No window size. No flags. No control bits. Yeah. 8 bytes. That's it. I'm not sure if it's the same in your NetAcad as well, but this slide is wrong. That row in the middle of the table, sequence number, yeah, that's a TCP thing. It's not a UDP thing. So make sure that you disregard it, basically. Now, another new concept, kind of new concept, but not different in the sense that we said from point A to point B, in order to communicate, you need 6 pieces of information with regards to addressing: layer 2, layer 3, and layer 4 addressing, source and destination addresses. Now we come to know a new concept, which is socket. Socket equals IP address plus port number. So you have a destination socket, you have a source or sender socket. Source or sender socket becomes source IP plus source port number. Destination socket becomes destination IP plus destination port number. Therefore, a pair of sockets together are enough to distinguish one app on host A from another app on host B, isn't it? So 2 sockets. And for those of you who have programming background, now it should make sense what we mean by socket programming, yeah, regardless of the language that you choose, programming language that you choose. At some point, if you're going to send and receive communication to network-based applications, you need to do some socket programming. This is what we mean by socket, yeah? So you define the port number and the IP address associated to that together. That becomes either your source or destination sockets. Pay attention to this slide. From left to right, this PC to this server is sending 2 different conversations. One conversation is FTP, if I see it correctly from here. Another conversation is web. You see how they can be distinguished from each other? So the user data is this. And then next to user data, think about OSI and think from top to bottom of OSI as data gets from the user towards the medium. So the very first encapsulation happens at transport layer by adding TCP port number or UDP port number to the actual payload, which is the user data. And then packets goes down to the next level, which is network layer. And then you add source IP and destination IP. You are doing encapsulation at network layer. And then the packet is passed down to Ethernet layer, where we do Ethernet encapsulation by adding layer 2 header and trailer. Yeah. So what distinguishes conversation on the top from the conversation on the at the bottom is the sockets. So destination IP plus destination port number, yeah, ignore the box that you see here. Destination IP and destination port number And destination IP and destination port number, there are two different conversations for this server, isn't it? On the same PC, source IP plus source port number is going to distinguish web traffic from FTP. Therefore, web app or web client app on the PC and FTP client software on the PC are distinguishable now, thanks to these sockets. Make sense? Crystal clear. So just in the same slide, so destination port number being 21, it means that you are talking about FTP. FTP uses two different port numbers, for destination port number 20 and for destination number 21. 20 is used for the actual data transfer, whereas destination port number 21 is used for maintaining a session, an FTP session, not TCP. Yeah, don't get it confused. An FTP session between the person A and the person B who want to share some file with each other. Destination port being 88 or 443 is going to tell you that you are talking to a web server. So this is a web query, a web request. We're going to see it in the next chapter, a GET request. Pay attention to the source port number. Source port number, most of the time, is going to be randomly generated. Because at the end of the day, you may have 10 browsers or 10 pages open. Yeah. So how to distinguish them from each other through transport layer? By randomly generating source port numbers. But destination port number is fixed. Either you're talking to a web server, or to an FTP server, or to an email server, etc., etc. When you want to communicate TCP, yep, go on.
I was just going to ask, in what situation would you want to use UDP, looking at how sort of unreliable it is compared to TCP?
VoIP, online streaming, voice over IP. So when you are broadcasting a video, let's say in 2-3 weeks time, Iran is going to play the World Cup against England. You're going to play that online. Yeah. So you don't go with TCP. It's going to be adding to your delay, and some content like voice over IP or online on-demand streaming videos, they are time sensitive. They don't tolerate any delay, and therefore you don't want overhead, and therefore you go with UDP, because what user cares about is user experience of seeing that football match almost instantly. Make sense? So for those applications, for instance, you go with UDP-based apps. You don't go with TCP. You don't care about reliability. You don't care if just one frame of the video gets lost while Iran is winning that game, for instance. Yeah, because it's just one frame that you're going to miss at the end of the day. The speed is more important. And for videos as such, when you're rendering those frames, we're going to have, let's say, 30 frames per sec. So if you just miss one frame, one lost frame there, you're not going to miss much. So those applications.
Sorry, so we're not using TCP because TCP would take or occupy all the bandwidth, which would make it very difficult to.
And adds to your delay.
Okay, but then, like you said, with the football matches, sometimes there are delays anyways, or maybe there's a glitch or it crashes or things like that, or maybe a bit of what causes that? Because if UDP doesn't carry as much, if UDP doesn't occupy as much bandwidth as TCP does, so why those occurrence, like I said, while streaming, and then there's like it's buffering or it's lagging or drops or things like that?
I didn't get the question.
So we're saying we're using UDP because it's best effort, right? It doesn't occupy the bandwidth compared to TCP, so which makes it easier to.
It's faster.
It's faster, but so what then happens? What happens when we have? What is the reason when we have lags or buffering or things like that or
So if
delays?
you send an email, you can't tolerate part of that email being missed. Whereas when you send an online video streaming like this football match, you don't care if one frame out of 30 in 1 second is lost. So one is faster, one is more reliable, depending on the application you choose either. Make sense? One, Maxim?
Just gonna answer this question, that's all.
Yeah, answer it.
Basically, it's because those are the frames that are dropped. So when you see like lag or something, those are the frames that are dropped. If it was a TCP connection, they'll go back and try and correct those frames. But because it's UDP, they're just dropped and it continues anyways. That's why you get like lags or like buffering.
Yep, good. But imagine that you do the same thing to address those lags with TCP. Then while the match is running at minute 40, for instance, you are what you're showing is minute 30. You're 10 minutes behind because of
I
the
see, I see.
overhead and processing and things like that.
That makes sense.
So you are not running this instantly. So pay attention to this scenario, for instance. From those two clients, we're going to send two requests to the server. One on the destination port 25, one on destination port 80, yeah, which is web request. What is important, so one is email, one is web, 25 is SMTP, and 80 is, or 8080 is HTTP. What is important is comparing this slide with this slide. So source port is randomly generated. Destination ports are fixed. But now if I go to the next slide, when you see the response from the server, you see that the position for source and destination ports are swapped. Source port now becomes destination port. So that random source port for the request or for the query from left to right, now in the response from server becomes destination port. And the destination port for the query, which was 80, now becomes source port. And similar change for SMTP. We talked about TCP being full featured, TCP being stateful, TCP being reliable, TCP being the best student for this module, everything. Now, we need to know how come that TCP is the best. I told you about three-way handshake that happens in advance of the actual data transfer. So before any segments being sent or received, the very, very first segment is going to be sent from source A to destination B, just a TCP segment whereby the scene flag is set. When I say the scene flag is set, you should remind yourself of TCP header. Yeah, bring back that note in front of you. So inside the TCP header, we had control bits, 6 bits. One of those 6 bits within that field is called sync flag. Sync for synchronization. So the very first TCP segment from A to B is going to have scene flag set. The sender is going to also choose the very first sequence number. Again, jump back to TCP header slide in front of you on Netacad and see the TCP header, so sequence number field. So let's say the sequence number that I want to choose is 100. Just before we move on, if you don't choose this randomly, then you are vulnerable to cybersecurity attacks. Because if an attacker can guess what your sequence number is, he can join in the middle of the conversation, impersonate that he is you, if he knows exactly the sequence number that you're using. So usually we go with random sequence number for the very initial TCP segment that we send as part of this three-way handshake. So CTL stands for control bits. You see the only bit within those 6 bits which is set at the moment from left to right is seen. So a seen TCP segment is sent from left to right. Now, next, B is going to say, hi, I have received your seen, so I acknowledge that. I send you ACK. By the way, I am also going to send you a seen to establish a two-way communication. Therefore, the second handshake out of three-way handshake is going to be sent from right to left by 2 control bits being set or by 2 flags being raised, seen as well as ACK. Pay attention to sequence number. Sequence number 300 is again the one that was initially selected this time by B. But what about ACK? ACK is 101. Remember, I told you acknowledgement number is always 1 plus what you have received. Yeah, I said that at the beginning of this lecture. Yes or no? So you see, you have received 100, you send ACK 101, saying that I have received up to 100, send me, or what I expect now is 101. So the left illustration just tells you the second way out of three-way handshake. So seen was sent from left to right, from right to left, seen and ACK. And then all is remaining is for host A to go back to host B with an ACK, saying that I have now seen your synchronization. And the sequence number is going to be 101, which B is expecting, and the acknowledgement is going to be 301. So 1 plus what I have received. And as you expect, the control bit which is set is acknowledged. So in short, seen and ACK. That happens to be a question that you may get in many of these interviews that you're going, yeah, for placement, etc., etc. So three-way handshake, how TCP establishes that initial session before the actual transfer of data. Any question on three-way handshake? TCP three-way handshake? Good. So what if I want to terminate the session? This is after I have established the session. This is after I have sent the actual data that I wanted to send through TCP. Now it's time for me to terminate that TCP session. TCP session termination happens with two-way handshake for each side, which together becomes 4 different messages being exchanged. From left to right, when A does not have any more data to send to B, will send a fin for finish message or a TCP segment whereby the fin flag out of those 6 bits control bits are set. B replies back with ACK. So similar to seen and ACK, here we have fin and ACK. But so far, only the session from A to B is terminated, not the session from B to A. And therefore, here, from right to left, you're going also to send another fin saying that B also does not have any more data to send to A and therefore wishes to terminate this TCP session. And A now needs to acknowledge that fin. So fin ACK from both ways. Make sense? Why do we need this three-way handshake with seen and ACK in advance of any actual data transfer? This is because we want to make sure that the recipient is there before we start sending the data. If we can't establish that three-way handshake, that TCP session, then the destination is not available. We can't send the actual data. Also later, as we are in conversation with the destination, we also want to make sure that the conversation is reliable. So later we may be sending some acknowledgement, we may be receiving some acknowledgement, we may be resending some lost segments, etc., etc. So all those things happens over this management session that we have established through three-way handshake. Just pay more attention to what is inside the control bits. Those control bits field contains 6 bits. The first one being urgent. If urgent is used, pay attention to bottom right hand side. You also have an urgent field, 16 bits long. Yeah. So if there is any content within that urgent field, then that urgent flag is going to be set. Meaning that it's going to be set to 1. Acknowledgement flag, you know what it means. So seen and act. You may have push flag. When it's set, it's basically, it tells the destination that as soon as you have read this, start processing. Don't wait for the end of the segment to be received and processed. As soon as you see push, hurry up. That's it. Reset is while you are communicating with B, so host A with host B, there are some errors happening and you wish to restart that session again. So resetting the connection. Seen bit or flag, you know what it means, and fin also, you know what it does. Yeah. One of the things that we have mentioned with TCP was ordered delivery. Pay attention to this slide. From A to B, from left to right, you send 6 segments. Segments may take different routes or routes to get to the destination, to get to the host B. You can't guarantee that all these segments are going to always go through one way only. Therefore, by the same token, they receive a destination in different order because they are taking different paths. Yeah. It's the job of TCP to make sure an ordered delivery. So segment 1, 2, and then 6, 5, 4, and then 3 are received in order, but they're out of order with regards to what the original data was. And therefore, they need to be re-put back into order before being delivered to the application layer at the destination site. What happens if some segments being lost? So from left to right, I wish to send 10 segments, and I send them. Segment 1 and 2 will be received. However, segment 3 and 4, they get lost. 5, 6, 7, 8, 9, 10 are received as well. The pure behavior or the very native characteristic of TCP is that when you don't receive segment 3, for instance, you go back with Act 3 and say that I haven't received number 3, I have received 1 up to 3, which is 1 and 2, and therefore now I am expecting segment 3, send me back segment 3. Why did I say the native or pure behavior? Because this is not efficient if you think about it. You have lost only 2 segments out of 10. But because that last segment happened to be at the very beginning of this communication, you are forcing host A to resend segment 5, 6, 7, 8, 9, and 10, while those segments were already received, yeah, without any problem. They were healthy, yeah, they were not lost. But you're forcing person A to resend those because of those 2 lost segments that you had, which is like segment 3 and segment 4. That was the behavior, that native behavior as I described. is called expectational acknowledgement method. By acknowledging 3, you are saying that I have received everything up to 3, which is 1 and 2, send me now 3. By acknowledging 11, you're saying that you have received 1 through 10. Now you're expecting segment 11. This is called expectational acknowledgement. But TCP also, for the recent implementation, works with what we know as selective acknowledgement. So expectational acknowledgement, selective acknowledgement. Same scenario. Host A is sending 10 segments from left to right, segment 1 through 10. Segment 1 and 2 will be received okay. Segment 3 and 4 are lost. Again, exactly the same scenario. However, host A and host B are running selective acknowledgement. What happens is that this time B comes back with this: ACK3, SAC 5 through 10. So ACK3 is telling A that next segment that I'm expecting is segment 3. Whereas SAC 5 through 10 is selective acknowledgement. It tells me that you don't need to resend those. I have already received those. They are healthy. Just send me anything between 3 and 5 through 10, which is 3 and 4, because acknowledgement is always telling you what he's expecting. Yeah. So 3 and 4. So I have received up to 3, which is 1 and 2. Send me anything from acknowledgement number alpha up to SAC beta to gamma. So from alpha to beta will be resent, but not all those segment 5, 6, 7, 8, 9. Therefore, you can see that selective acknowledgement is more efficient than expectational acknowledgement. Yeah. Another concept we've gone through earlier is flow control. Basically, on the sending side, you're going to have a window. Window is the number of bytes, or determines the number of bytes that the sending TCP application can send at each time. Window is a dynamic concept. It gets larger or it gets shrink depending on the rate at which he should speak with the destination. Who determines that rate? The receiver or destination. Because if I'm talking too fast or if I'm talking too slow, you should be telling me as the receiver or listener that you're talking too fast. Can you speed down or speed up otherwise? Yeah. So exactly similar concept happens to be here. Pay attention to this slide. This one is very important. So also I had a query earlier about the assessment for this module. For the first semester, the assessment is going to be exam. It's going to be written exam. You come here and it's not going to be on machines here. You're not allowed any notes. So you are not allowed headphone. Therefore, you can't just make fun of other things while you're sitting here. Therefore, you need to use your lovely hand, pen, and paper. You will be sat in the way that I usually sat my students, usually with 100 kilometers away from each other. And you will be having some invigilators sitting next to you who are going to accompany you even if you go to bathroom. And therefore, no way of cheating unless you come up with some new ways. And then you will be given questions on those papers. And how difficult or how easy those questions are going to be exactly around the end of chapter bundle questions that you do with on NetAcat. And therefore, you're going to have a combination of theoretical as well as practical questions, so commands, labs, NetAcat, concepts, slides, etc., etc. Basically, you know my way of running these assessments. So anything that we have explained is going to be part of the assessment. Yeah. Any question on the assessment? So formative assessment for this module is the end of chapter exams that you are supposed to be doing each week. That I'm sure you will be doing for the first 10 chapters by next week. I had I don't need that. I don't think that I need to repeat this, but I had a student who thought he's very cool and who turned up in digital technologies module last week because Master ran the part of the assessment for that module earlier than end of the first semester last week. So he turned up half an hour late, and he thought that he can just join the session by saying sorry or things like that. Even if you go 1 millisecond, not half an hour, 1 millisecond after any deadline for summative assessment, yeah. So you know what summative assessment means, yeah? Those assessments that have bearing in a sense that you will be assessed and that mark remains within your transcripts, yeah? Those are called summative assessment, usually happens at the end of each semester. So it can be in the form of Blackboard submission, it can be in the form of the assessment you come here, it can be in the form of group assignment or group presentation, etc., etc. Those summative assessments that bear some mark with themselves, yeah? If you come 1 millisecond or if you submit 1 millisecond after the deadline, you are marked 0, failed for that module. So that's me, not me again, that's the university rule. Make sure that you plan in advance. So we already talked about size for different layers and what it means for different layers. Here at transport layer, we also have maximum segment size known as MSS. What is the maximum segment size? The rule is this. For TCP, because segment is a TCP concept, yeah, no surprise. For TCP, to calculate MSS, what you do is this. You see the size of the Ethernet frame minus the size of IP header minus the size of TCP header. I'm sure you are making notes then. So MSS size is the Ethernet frame size minus IP header minus TCP header size. What is the Ethernet frame size? The default one? Anyone? 2 weeks ago, the lecture? MTU, if you remember. Those concepts, maximum transmission unit. So it's 1,500 bytes minus. What is the header size for IP? IP4? 20 bytes. Minus. What is the size for TCP header? 20 bytes. So 1,500 minus 40 becomes 1,406. This is maximum segment size. That simply means that at each go, A to B can send up to 1,460 bytes. Yeah. What is window size then? Because remember, we're talking about the flow control. Window size, look at the board, is this, or even is this. How many go I can have before expecting acknowledgement? Can I have 3 goes? Each go with MSS maximum? Can I have 2? Can I have 10? You see the size, the window size gets larger. So what determines this size? Receiver. Telling me that you are speaking too slow. You can maximize your window size, meaning that you can go 10 go before expecting one acknowledgement. Or you're talking too fast. Yeah. So please speed down, depending on what receiver says. So that is window size. How many bytes I can send before I expect an acknowledgement. From left to right, I start with sequence number 1. MSS tells me that you can send 1460 mute yourself. I send the first go, and then I send the second go. You see the acknowledgement number? It comes back with acknowledgement 2921, which is one more than what I have received, which is basically what now I expect. This is the acknowledgement number. At all those TCP exchanges, the window size field is there. Yeah, recall the TCP header, the fields inside TCP header. And therefore, that window size is negotiable dynamically through your conversations between those two ends. Now that I have talked about window size, you should know also that the devices today, they are going to use what we know as a sliding window. Shouldn't be a surprise. I think I showed you on the board what it means by a sliding window. So as it gets shrinked or as it gets larger, depending on the proper rate for the conversations. This is also about MSS size, maximum segment size, how we determine it. Next slide is very important. So pay attention to the size for Ethernet frame. That's from bottom of this slide. It excludes the Ethernet frame header and Ethernet frame trailer. It only contains from here to here, yeah? Those 3 middle boxes. Then you're going to have MTU, if you remember from 2 weeks ago, yeah? Maximum transmission unit, IP or Ethernet. It is, again, those 3 middle boxes. However, when we are talking about TCP MSS, we are only covering payload of the communication. You see the span for TCP MSS? And that's why I told you how to calculate the value for TCP MSS. You say maximum size for Ethernet frame, which is 1,500, that MTU, minus the header size for IP, minus the header size for TCP, which happens to be 1,500 minus 20 minus 20, which becomes 1,460. This is how we calculate. Why? Because we are interested with TCP MSS about the payload. If you remember, so far with lower layers of OSI, we disregarded the payload itself as such. We were more into Ethernet header, IP header, and how to deal with them, the fields inside it. But TCP is going to basically encapsulate the actual payload. And therefore, there should be a mechanism to discuss the size of that payload. And that mechanism comes in the form of MSS. And this is how we calculate MSS. Your CCNA does not go through details of congestion avoidance. It just tells you that there are some mechanisms, some algorithms, and some timing around it. You know what congestion is? Congestion, or how to avoid congestion with regards to TCP, becomes more important in a sense that imagine that PCA is going to send traffic over TCP to PCB. However, because of some congestion, some of these segments get lost or will not be delivered in time. And therefore, PCA needs to resend those lost segments, isn't it? That's the very nature or natural behavior of TCP. However, because the link is already congested, those resent segments are going to add to the delay. They are going to make the situation worse as with regards to congestion. And that's why there is a slide here just telling you that be careful about congestion. And TCP itself has some algorithms to detect that if there is congestion, I shouldn't be sending those lost segments blindly, or those segments that I think are lost might not be lost. It just might be delayed because of the congestion. I shouldn't resend them. So there are some mechanisms, but at CCNA level, we don't go through them. So there is a lab on Nmap that I'm sure you're going to do and come back with the solution to me next week when I want to check on everyone. Lamek. Was Lamek here? Yes or no?
Yeah, you said so, bro.
Hi, Lamek. Why are you sitting there? 1 million times I told you not to sit there. That's fine for today, but don't sit there. Don't hide yourself from me.
I came in a bit late, so.
I know that I'm going to make you late rather than absent. But don't be late. So,
Right.
remember, guys, I used to teach MOD, and believe me, I know how to deal with you. So, for next week, which is week 8, Milo, you're going to present chapter 11. And 12, Milo. Yeah? Yeah. And Elvis,
Yeah.
you are going to also present chapter 11 as well as 12.
Okay. Cool.
Thank you. So, next chapter is about network services. We have built up from bottom to top all these OSI layers, one on top of each other. And we have reached network services. At the end of the day, all these OSI or TCP/IP layers are there to facilitate and realize these network services being running on our network, providing some facilitating or performing some tasks for us. Tasks to do with IP address assignment, as with DHCP. Tasks to do with domain name server or domain name system, whereby names are translated to equivalent IPs. Tasks to do with network address translation, NAT, whereby private addresses are translated to public IP addresses. Tasks to do with file sharing and sharing services. Tasks to do with emails. And finally, tasks to do with web services, providing web resources to web requesters. DHCP can happen in two ways, dynamic or static. Dynamically through DHCP version 4 protocol or DHCP version 6 protocol, depending on the IP version that you have, or statically through you going to your network network and sharing center on your Windows, for instance, or on your Linux with some commands to assign IP addresses manually and statically to your network interface card. It's not the case that we always go with DHCP because it's easier and because we are lazy. Sometimes for, let's say, some web services, for instance, for some servers in particular, for default gateway, for certain firewalls that you have, scenarios like that, you may want to know exactly what has been assigned to what. So which IP has been assigned to which device. And therefore you go with the static IPs for certain cases. You don't want network devices to wander around what the IP address, for instance, for their server is or for their printer is. Whenever we learn a protocol, the very first thing that we need to learn is its operation. Like ARP, for instance, you have learned it before. The DHCP operation happens through what we know as DORA process in short. D for discovery, O for offer, R for request, and A for acknowledgement. DORA, yeah, DORA. So a client comes up. As soon as it comes up, it needs to ask for some IP address from the server. The way that it works is that the client is going to send DHCP discover message. This message is sent in broadcast. Why in broadcast? Because it might be the case that we have more than one server in that domain, and therefore we want all those DHCP servers to receive. We want to shout out so that everyone can hear us. And the closer the DHCP server, of course, will respond to us quicker and let us know that, hey, I've heard you, and this is the offer that I have for you. With the DHCP offer, the server is going to go and find one IP address within the pool of IP addresses, which can be leased. These words are technical words, yeah, which can be leased for certain period of time, let's say for 7 days, for instance, to this client. The DHCP offer is going therefore to be a unicast answer to that DHCP discover message. This DHCP discover was broadcast. And if the client is happy with this university offer, he loves this university, for instance, is going to say, yes, I'm going to accept this offer. DHCP request is going to be sent from left to right. And then we're going to say DHCP ACK. Again, DHCP ACK is going to be sent by the server to the client. The DHCP offer also, DHCP request also is going to be a broadcast. These are the basic forms of it. It can be other forms. It's not always broadcast, but also in this case we go with broadcast for the request and acknowledgement. So it might be DHCP NAC. However, if it's NAC, we're going to cancel our previously offered IP address to the host because it's not available anymore. For instance, we have given it to someone else. Next is going to be the message format for DHCP. So you see all those fields happen within the DHCP message, from the opcode, hardware type, hops, transaction identifier. But what is important for me is the client IP, your IP, that me as the server, for instance, I'm going to offer to you server IP, gateway IP, boot file name. So you don't see this boot file name field usage much these days. But in the past, we had scenarios whereby even the boot file was not located on terminals, was not located on these PCs, for instance. The boot file was located somewhere else. As soon as a machine or a terminal, we call it because it's an old kind of topology, comes up, they would ask for where the boot file is. And then this DHCP not only provides IP addressing for them, but also telling them where they can get their booting file from, if it makes sense. So all those are included in DHCP message. Next network service is DNS, domain name system. From now on, you see that many of these client-server architectures, many of these network services are based on a hierarchy of servers. Therefore, if the closest server to you cannot provide the answer to you because it does not have the right answer to you, through that hierarchy, servers in turn are going to be contacted until we find the right answer to your query and come back to you. So DNS is one of those protocols that operates based on this. I have covered this before. You don't need to spend time on it, what DNS does. So basically you put a URL or what we know as fully qualified domain name in the form of English letters there, and then it's going to be translated to some IP addresses because machines, they work with numbers, not with names, and therefore everything at the end of the day should be binary 0 and 1, or should be numbers at least. This is the domain name hierarchy or DNS hierarchy that I was talking about. So from top to bottom, at the very top, we've got the root. Then next level from top to bottom is going to be what we know as TLDs or TLD servers, top level domain servers or top level domain DNS servers. And then below that, you got the secondary level domains. And then finally, you've got separate servers, one taking care of, let's say, file transfer. So FTP server, one taking care of email server. So pay attention to how that hierarchy is built. For instance, ftp.cisco.com, how it fits within this hierarchy. From top to bottom with TLDs, that .com part is identified. And then with secondary level, cisco.com is identifiable. And then with the below level, the ftp.cisco.com is identifiable, isn't it? Therefore, if I put in my browser, as soon as my machine boots up and I get an IP, I open up a browser and I put ftp.cisco.com. How the IP packet is formed? Well, that URL needs to be translated to some IP in order to put that into destination IP in my IP encapsulation, isn't it? How it is formed? I'm going to go and query. Imagine that I don't have any information in my cache. My browser does not have such information in its cache. My current ISV DNS server does not have any such info in its cache. Yeah, we have no clue at all locally. Therefore, I'm going to go and query TLDs about .com. And then TLDs are going to query secondary level about Cisco.com. And secondary level servers are going to query FTP. And then at that point, that guy is known to be what we know as authoritative DNS server. Authoritative DNS server is the person who holds the first-hand information in its hands. The first-hand information about that domain to IP mapping. That guy who has such authoritative information comes back to us. That authoritative information in hands of that authoritative DNS server is known as resource record. So resource record is another terminology within DNS. Yeah. So that resource record now can be shared with us. But what happens in reality is that many of these websites that you are searching for, your browser is, at the end of the day, is a client application. Within itself, your browser knows about the famous websites and the mappings or where to contact and things like that. Yeah. Otherwise, they need to go through this process and find out who is dealing with that. So exactly the process that I have described for you. So nothing new here. So from left to right, how the DNS queries go and how the DNS replies come back, how they are searched. So FQDN, fully qualified domain name, is what you put in your browser. And next step, a DNS query is going to be sent. And then the mapping between FQDN and that IP address is going to be found in one way or another, depending on the DNS, the right DNS within the hierarchy, which has that first-hand information, and is going to come back to you. That's it. You're done. DNS uses UDP port 53. No surprise, because we want DNS to be very fast, isn't it? We don't want it to operate like with with like emails, etc. So this is the typical implementation. So some implementation for other protocols, for instance, they use TCP as well. But the typical implementation for DNS here uses UDP port 53. All the communications for any protocols happens through what we know as exchange of some messages. Messages, depending on the protocols, can have different names. Interestingly, for DNS, that communication itself is also called a message. So message itself is a meaningful term within DNS context. This is what you see within the context of DNS. Yeah. So the fields include question, answer, authority, and additional. What is important for you at this stage is question and answer. Question, as the name suggests, tells you that I am after www.wahidhaidari.com. Do you know the mapping or the IP for it? And the answer is going to be a message that you're going to receive sent by some authoritative DNS server saying that, hi, yes, I know him, and this is his IP. Additional, well, this name to IP address binding is not just as simple as that. You're going to have additional information also bound to those mapping. Additional resource records information is going to be put into that additional field of DNS message if required. We have something called dynamic DNS as well. If you read NetAcat, you're going to be very confused about what dynamic DNS is or what dynamic DNS means. Therefore, everyone quickly watch this video. I'm going to ask you if you understood what dynamic DNS is after watching this video. Let me see if I share this lovely video on here on Teams. Can you see my YouTube on Teams? Yes or no?
Yes.
So that's what we're going to talk about in this
Can
video.
you hear the voice as well?
Yeah,
That's
we
good.
can.
So let's watch it together.
What is DDNS? So that's what we're going to talk about in this video. Now, DDNS stands for Dynamic Domain Name System. Now, I previously did a video where I talked about DNS. And if you're not familiar with what DNS does, I highly recommend that you watch that video also. And you can find that video on my YouTube channel. But in this video, I'm going to talk about dynamic DNS. So just as a refresher as to what DNS does, if you type in a web address in your web browser, DNS is what transforms that domain name to an IP address. So for example, when you type in youtube.com in your web browser, the DNS server will search through its database to find a matching IP address for that domain name. And when it finds the IP, it'll transform that domain name to the IP address of the YouTube web server. In a DNS database, a domain name such as youtube.com is mapped or joined to an IP address. And that IP address must not change. In other words, it must be a static IP. Because if YouTube's IP address changes to a new IP address, people will not be able to access YouTube's website because youtube.com is still joined to the old IP address. So if the IP address does change, DNS will update their database with the new IP address for youtube.com so people can find YouTube. Now this may not sound like a big deal. However, the problem is that it could take up to 24 hours for DNS to update their database with the new IP. And that is a problem because that means that YouTube will lose up to 24 hours worth of business until DNS does the update. And this is the main reason why websites, organizations, and companies use static IP addresses and not dynamic IP addresses. So DNS is used with static IP addresses, but dynamic DNS is used with dynamic IP addresses. A dynamic IP address is where an IP address gets an IP from a DHCP server. Therefore, the IP address changes periodically. Dynamic DNS is a service that allows you to access devices that are in your home, such as a computer, router, or security camera, and you can access them from anywhere in the world, even if your IP address changes. Dynamic DNS is mainly used in homes because internet services that are used in homes are given a dynamic IP and not a static IP. So let's do an example. So let's say you're at work and then you wanted to access your home computer using Microsoft Remote Desktop. So you would open up the Remote Desktop service from your work computer and then you would type in the IP address for your home. And then you would type the password and then you're connected. So you already knew what the IP address was for your home because you either wrote it down or maybe you memorized it. However, since you have a home account with your internet service provider, your IP address is dynamic and it will change periodically. And if it changes without you knowing about it, the next time that you want to remote access your home computer, you will not be able to because you're typing in your old IP address and not your updated one. So this is where dynamic DNS comes in. Dynamic DNS allows you to access your home computer even if your IP address changes. It allows you to create a custom hostname such as myhomepc.ddns.org.
Now look at the slides in front of you and you should be able to see the custom host name. Yeah, the custom host name for this example that Cisco has provided. Yeah, go
or
on.
whatever. And then you can link that host name to your computer. So if your home IP address does change, Dynamic DNS will update the new IP address and map it to your custom host name automatically. So Dynamic DNS will ensure that you will always have access to your home computer even if your IP address changes. So for example, now let's say you wanted to access.
So copyright for PowerCert animated videos. They're good guys providing these professional videos and we can make use of those videos. So just let me bring up the previous discussion that we had. We also have another protocol called WHOIS protocol. WHOIS protocol is interesting for attackers as well, because it helps them with their reconnaissance stage as well. Basically, WHOIS protocol is going to query the ownership of a domain. Who has registered this website? What is their email? What is their identity? How to contact them, etc., etc. Again, a honeymoon, if you think about it, for an attacker who wants to do some reconnaissance around that targeted website. So there are many applications that work and operate based on this WHOIS protocol to query the ownership for different websites. ICANN look up, well, ICANN itself from last year's module, if you remember, we've gone through this, is going to be the institute under the umbrella INA organization, which takes care of naming and numbering for the internet. Yeah, the IP addresses and the domain names, etc., etc. So ICANN has this ICANN lookup tool which operates based on WHOIS protocol, allowing you to query the ownership of the website and start getting some information about the owners. Another network service is network address translation. RFC 1918, if you remember, tells you the private ranges, IP addresses that should not appear anywhere in the internet apart from hidden behind your LANs. The reason is that they are not routable, and therefore we call them private IP addresses. Each company is going to be assigned one or a few public IPv4 addresses. So the company is going to go and purchase it. So money is involved. And then all those sitting in that company behind the border router are going to be assigned with private IP addresses. Once they're going to reach outside world, those private IP addresses are going to be translated to those few public IPv4 addresses. This is what we know as NAT translation. As I said earlier, it happens at the border router for that organization. You're going to have a NAT pool. Again, the word pool here. So whereby these private IP addresses are going to be translated to public IPs. From left to right, this is going to send some traffic to that server. The PC, as you can see, is assigned with private IP addresses from 192.168 range, as you would imagine. Then the company at its border router is assigned with what we know as inside global, 209.165.200.226. So the source, the very source IP address for the packet generated by the PC is going to be 192.168.10.10, and the very end destination IP address, is going to be 209.165.201.1. As the packet gets to the border router, which is R2, for instance, in this case, that source IP is going to be changed. It's going to be now what we know as the inside global. It's going to be 209.165.200.226. The destination IP is going to remain the same, 209.165.201.1. And then the packet will be sent. The response from server to PC is going exactly to have the same pair of IPs, but change in a sense that destination is going to be 226 and source IP address is going to be .1. When it gets to the border router, At R2, again, it's going to be having the 192.168 as the destination IP. So the previous destination IP is going to be stripped off by NAT router. So that router is going to be NAT router, or network address translation router. Next to NAT, we also have what we know as PAT, port address translation. So if you think about it, if in addition to IP, that border router can note down the port number from which it received an IP packet, or a packet basically, then it can address more and more users, and therefore they can need less and less public IPs, because that combination of IP plus port is going to be very much unique and distinguishable between all those packets and between all those local area network machines who are going to reach outside world. So PAT does the same translation, considering IPs as well as port numbers. Next service is going to be FTP, File Transfer Protocol. It's a TCP-based protocol. FTP uses two different TCP ports. I have gone through this already. So TCP port 20 and 21. 20 is going to be where the actual data communication happens, whereas 21 is the control session, so control connection, over which the data connection is going to be established. FTP, as I said, has a UDP-based sibling as well, TFTP, which is faster but unreliable, operating on port 69. Next one is file sharing services with Microsoft. Microsoft has developed this protocol, SMB, server message block. It works, or it is known as the mainstay with Windows-based networks, in a sense that if two machines are both on the same Windows domain, and if they are shared using SMB, server message block, you can open up a browser on the PC and from the left, as if you are on the PC from the right, by putting their address there, and then you can start copying, pasting files, similar way that you copy and paste files on your own local machine, thanks to SMB. So it also allows for authentication, which is good for security reasons. Another protocol, or another set of protocols, SMTP, POP, and IMAP. I have gone through this. The difference was SMTP is going to be used for sending emails, whereas POP and IMAP are used for receiving emails. So similar to DNS, as I told you earlier, a hierarchy of servers are going to facilitate what we know as email system in the world. Each ISP or each zone or each domain is going to have one or a couple of email servers there. And when you want going to send an email using, let's say, your email client application like Outlook, you're going to place a copy of that message into the closest SMTP server. And that SMTP server is going to get in touch with the next SMTP server up until they get to the closest SMTP server sitting next to the recipient, and place a copy of that message for him, so that as soon as he comes up, as soon as he logs in and opens up his Outlook client software, he's going to receive or retrieve a copy of that. Receiving or retrieving a copy of that email happens through two protocols, POP or IMAP. The difference is that with POP, you are not only receiving or retrieving that email address or a copy of that email address, but also you are removing the original copy from that server. Whereas with IMAP, you just receive or retrieve a copy of that email address, and that's it. The original copy of the email message is going to remain there. SMTP operates over TCP port 25. I've gone through the process. POP operates over TCP port 110. Again, I've told you what POP does and how it is different from IMAP, so shouldn't be any new concept for you here. Next one is Hypertext Transfer Protocol, HTTP. Don't confuse HTTP with HTML. There are two separate stories, hypertext markup language. HTTP is the network service or network protocol which enables exchange of web pages. Those web pages themselves are interpreted in their exchange by HTML code. So HTML is a code through which we describe the content of a web page. That content being text, that content being sound, being video, being images, etc. So when you open up your web client browser, so I just said that HTTP is a client-server based application, isn't it? So when you open up your web client or your browser, which is a web client application, you're going to put the URL there. The URL comes in the form of this, what you see in this slide. So from left to right, first of all, you're going to have the scheme or the protocol, HTTP or HTTPS or FTP, etc., etc. Then you're going to have the domain name, isn't it? And then with colon, sometimes you're going to have the port number next to this. So because it might be a couple of port numbers expecting client queries or client requests. Therefore, port number sometimes is there as well. And then on that server, you're going to specify the path from which you are inquiring about a resource. You have two characters here. One is the question mark, another one is the pound character. The question mark is usually placed before pairs of name and values that we have. Here we are saying that under this sounds path, I am after this document ID. So you see doc ID is going to be your name, and then the value is the number in front of it. And then you have the ampersand. Then you're going to say another pair. So name and a value, format equal MP4. Apparently this sound file type is MP4, what we are after. And then you see the pound character. Pound character is also going to specify the fragment within that query. So that fragment can be the minute or the second of that sound file that we are requesting to get access to on that web server. So this is what you put, or this is what a full URL means. And then a HTTP GET request is going to be generated. It's going to be sent to the server. And then if server can find that resource, it's going to send it back to you in the form of HTML code. Your browser, which is your client application or your web client application, is in fact the software or the process that can interpret that HTML code, render it properly to what the user should be seeing. This is the beginning of the form. This is where images are. This is the sound. This is etc., etc. So HTTP GET request is not the only HTTP message type that we have. We may have put, we may have post, delete, options, connect, post and put. For instance, when you are filling out some form, or for instance, when you are uploading some multimedia file like images, etc., into your email server, you're going to use different message form. We're going to also have a status code with HTTP. Basically, the server is going to come back to you and tell you what is the current status of your HTTP query or request. Anything within the range of 200 is okay. Yeah, anything within the range of 400 is not okay. The very famous one, yeah, 404. The resource that you are after is not found, and the server is going to come back to you with the status code 404, saying that this resource does not exist, or I cannot find it. So anything within 400 is going to be problematic, but the lower the number, like 100 something, is going to be more informational. Another top tip for cybersecurity student, these status codes that some web servers and some web services are generating are sometimes providing too much valuable information for the attacker. Does that make sense? And attackers can basically map out what the network or what the system is based on these information or status codes that HTTP servers sometimes are providing. So this is something to consider. We get to that later as well. That was pure HTTP 1, or the first version of the protocol that I have talked about. HTTP version 2 operates based on the same status code, based on the same messages type like get, put, pull, etc. However, one difference is that while HTTP version 1 was treating those different queries for resource page, for resource.html page, resource.png image file, etc., separately or independently or individually. With HTTP 2, you are able to mix those guys together over one TCP session. So that was an improvement with HTTP 2 compared to HTTP 1. Then we had HTTPS, whereby the encryption was added. HTTPS operates based on SSL or TLS, so secure socket layer or transport layer security. You're going to have encryption as well as authentication with that. I think I've done great in the sense that I've covered the main points that I wanted to cover in right time. So